So this is take 2 of solving this sample final 3 of Math 2A. So the reason I say take 2 is because some of the problems I just did not understand, because some of them were written really poorly, so you might hear me complain during this video of how poorly some of the questions are written. So whoever did this, honestly, did a bad job of making this final exam, sample final exam. But anyway, let's continue solving the problems. Okay, and then you can, maybe me complaining about anything that's unclear is helpful to for you guys to understand what's going on some of those hard to understand problems also, okay? So let's move on. Here we're given this function. We're asked to find f prime x and f double prime. That's easy, this is not an issue. F prime, we need product rule, first d second plus second d first. First, d second, that's a minus sign, plus second d first. Okay, so that is the first derivative. We can even rewrite this as, we can factor out e to minus x. That'll just be 2 minus 2x. Okay, or you can even 2e to minus x, 1 minus x. Factor it like that. Okay, f double prime x, we need the derivative of this guy. Again, first d second plus second d first. First d second, that's just minus 1, plus second d first, that's minus 2e to minus x. So we can, once again, factor, but let us, this would be a minus. Let's distribute first to see what's going on. Minus 2e to minus x plus x e to the plus 2x e to minus x. Let's check I did this right. Minus e to minus 2x, that's fine. Distribute this guy to here. That's just minus 2e to minus x. Distribute this guy to here. That's plus 2x e to the minus x. That looks right. This would be minus 4e to minus x plus 2x e to minus x. Okay, and again we can factor a 2e to minus x. We can factor that out. We would get, this guy would just be x. This guy would be minus 2. Okay, so there's a f double prime. Here's a f prime. Okay, and there's a reason why I wrote it like this, because of this next part. Absolute slash local min, absolute slash local max. So how do we do that? First derivative. We know that there's a critical point at x is equal to 1. Okay, so we draw a handy dandy number line. At this point is 1. When x is less than 1, remember our domain, we are given this domain. I didn't mention that when I started the problem, but we're given the domain of 0 to infinity. So technically, like this, okay? Between 0 and 1, what's the sign of the derivative? So for example, if you plug in half, this guy would be positive. Exponential is always positive. This guy would also be positive, so plus here. Next, we plug in a big number like 100. This guy would be positive still. This guy would be negative, so we have a negative sign there. Okay, so we know that we have a local max because changed from positive to negative, derivative changed from positive to negative, meaning function increased then decreased. So we know that that's a local max. At point 1, what's the value of the max? Well, we plug back into here. When x is 1, that's 2 times 1 times e to the minus 1. So that's just 2 over e. That's a local max. We don't have any local min, but do we have an absolute min? Okay. The trick here is, notice the domain, 0 to infinity, okay? So we know that starting at 0, what's the value of 0, 0? So let's do it on the side. When x is 0, this guy is simply just 0, okay? And then it increases until 1, so obviously this is smaller. And then it reaches this maximum value, and then it decreases again. Okay, so we know that this guy, 2x e to the minus x, because as x goes to infinity, this guy would go to infinity, right? But e to minus x would go to 0, okay? So it's kind of like inverse. One will be going bigger, one will be going smaller, okay? So eventually, the exponent will dominate, and this guy would approach 0. Okay, so notice I said approach 0. This guy is at 0, but as you go from 1 to infinity, the function should approach 0. Okay? Luckily, this says no work needs to be shown, so we can just say that the absolute min is at 0, 0. Okay? Intervals of increase, we just did that. That is from 0 to 1. Intervals of decrease, that's from 1 to infinity. Okay? Inflection points, well, that's when we use the second derivative test. That's why I wrote it like that. We know we have a critical point as x equals to 2, so we check there. We do a handy-dandy number line. Okay? So when x is between 0 and 2, so for example 1, the second derivative would be negative. And then when x is bigger than 2, for example, a big number, 100, this guy will be positive, that's always positive, positive. Okay, so we know we have a point of inflection at x is equal to 2. What's the value of f of 2? That's just 4 over e squared. Let's just plug in 2 into f of x. Okay, so that's that. Concave up, we know that it's concave up from 2 to infinity. And we know that it's concave down between 0 and 2. Okay? Horizontal asymptote, we know that there is a horizontal asymptote because, remember we were saying e to x, and that has an asymptote, so it should be y is equal to 0. Vertical asymptote, this guy has none. Okay? Okay? Now we're asked to sketch f. Okay, so we have this whole table here. Let's help us out. This should help us out. So we said there is a max at x is equal to 1. And well, actually, first of all, there's a point 0, 0. That's where it starts. There's a max at x is equal to 1. The value is 2 over e. Okay, so we'll have a point there. Okay, and then we also have an inflection point at 2, 4 over e squared. So let's say 4 over e squared is here. You do know that 4 over e squared is smaller than 2 over e. Okay, so it should be smaller. This is just sketch, so it doesn't have to be to scale. We know there's a point of inflection there. Okay, so we know from here points of intervals increase 0 to 1. It should increase to here. Okay, and then afterward it should always decrease. We know that from 0 to 2 it should be concave down. So it should look like that. This is concave down, correct? And then after 2 it's concave up. So it should look something like this. And we know we have asymptote as y equals 0. That's how f looks. Okay, so that's how we solve this problem. Limit definition to calculate derivative of 1 over x. I've done this many times, I feel like. Let's do it once more again. A prime of x is limit as h goes to 0. This is a limit definition. X plus h minus f of x over h. Okay, so that's just limit as h goes to 0, 1 over x plus h minus 1 over x over h. Okay, don't drop the limit sign. Limit as h goes to 0. Remember how we do this? We want to make one big fraction. Okay, so we would get, when we distribute, we have x minus x plus h in parentheses over h, x plus h, x. Okay, and then we get limit as h goes to 0 of minus h over h, x plus h, x. This x and x would cancel. This would cancel. Now we evaluate the limit. That's minus 1 over x squared. And by this point, you know the power rule. This is x to minus 1, so minus 1, x to minus 2 power. We confirm this is correct. Okay, so I did that quickly. I've done this in many other videos, so hopefully you can watch those if you didn't get that. Okay, this is the bad question, one of them. Okay. The profit made by Easy Motors when it sells n cars is given by a function p of n. Suppose when n is equal to 100, that dp is 1,000. Which of the following sentences must be true? Circle all that apply. Okay, this is bad because it doesn't say that dp is a differential. Okay, it assumes that you know that. But this is just, dp could be just any variable. So this is very vague. So I got confused by that. Okay, so let's write it down. It's a differential. Okay. So what is differential? Remember this, you learned in the section of linear approximation. And remember what a linear approximation is? Let me just draw it one more time and explain. We have a function f. We know the value of the function. We know f of a at x is equal to a. We don't know what f of b is at some nearby point x is equal to b. So we can use the tangent line at x is equal to a to approximate f of b. There's just a small error, but it's an approximation. And then, of course, as b gets closer to a, your approximation gets better. Okay, so that's the idea of linear approximation. Same thing, similar concept for differential. We're going to use the instant rate of change at x is equal to a, and then we'll use that to approximate f of b. Okay, so that's how we do this. Again, this is unclear that dp is a differential. It should, honestly, it should explicitly say that, otherwise it's just some other variable name. Okay, so bad question, whoever wrote this. Anyway, let's solve it as how they probably intended to. Okay, so you're given all this. I got lost also reading all this. So what actually helped was, let's start with point C to see if this is true. If P of 100 is 50,000, then P of 104 is approximately 54,000. So let's say N, let's draw a table of values, P. Okay, so if N is 100, then P of N is 50K. Okay, 50,000, I'm just going to shorthand 50K. Okay, so by the differential, when we increase by 1, okay, then that means this P of N approximately is 51K. You take one step in the N direction, you get approximately a change of P of 1,000. That's what the differential is. That's what the linear approximation is. Okay? 102, that's about 52K. So when you go to 104, that's 54K. So this is correct to say. The rate of change of P of N is 1,000 over 100, which is $10 per car. The rate of change of P of N. I don't no idea why they would get this, but this is the rate of change of P at N is equal to 100. So this is not even close. So it's false. Okay? The P is the rate of change. That's false. We don't circle that. If Easy Motors sells 97 cars, then it will make approximately 3,000 less profit than if it sold 100 cars. So let's keep using this scenario. So if it was 150K, so let's go in the other direction. So for example, if it's N is 99, then it's about 49K, right? So then at 97, it will be around 47K. With respect to 100, that's 3,000 less, so this is true. Okay, and if Easy Motors sells 102 cars, so let's use this example again, then it will make exactly $2,000 profit. So remember, we said this is just approximately 52,000 because we're using this differential to estimate. Exactly 2,000, not likely. So false, we don't circle that. So only B and C are true. Okay, so again, I'm going to complain one more time. This differential is unclear. They didn't say that it's a differential, but I assumed you know that. So that's the idea for this guy. Okay, whoever wrote it, again, not a good test writer for this particular problem, at least. Okay, let's move on. True, false for these limits. Okay, and we have to show work. Okay, so how do we solve the first one? Remember, this is just a horizontal asymptote, so you can eyeball it. Remember how you eyeball it? Just take the just do the degree test. The square root is just half the power. So that's just x to the third over x to the third. 3x to the third, so same degree, so take the leading coefficient, it'll be plus minus 1/3. So this is probably likely asking us to find if it's plus 1/3 minus 1/3. We just have to confirm. Okay? So how do we solve this? Remember, we like things in 1 over x, or 1 over x squared something, because when we take the limit as this guy goes to x goes to infinity, this guy goes to 0. Okay, so how do we solve this? We want to make it in terms of something like this. So on the top, we factor out x to the 6. Okay, so we factor out x to the 6 inside the square root. And then on the bottom, we factor out x cubed. Okay. So remember, we can split up a product of two limits. So we can manipulate it to be like this. That's infinity of whatever is left. 1 plus 5 over x to the 5th plus 9 over x to the 6th over 3 plus 2 over x cubed. Okay, so when we take this limit over here, that's easy because it's the limit to infinity. These guys would go to 0. We are left with 1/3. Okay, and then this guy is, since we're going x to minus infinity, this guy is the same thing as minus x cubed. It's the minus sign because we're going to negative infinity. So this limit would just be minus 1. So our answer should be minus 1/3. This is positive 1/3, so that's false. Okay, so that's how you solve that problem. I've done similar problems in previous videos, so you can look for more for there. This guy, let f of x is equal to x squared. There exists some c in the interval 2 and 4 for which f prime of c is equal to 6. So this is asking for mean value theorem, it looks like. Okay, so what does the mean value say? F has to be differentiable in this region. So we know f is differentiable. Okay, and we can even say f prime of x is equal to 2x. Okay, so f is differentiable. Because of that, we know that, what does the mean? So f of 4 minus f of 2 over 4 minus 2. This guy, mean value says there's some value c which equals to this guy, okay? F of 4 minus f of 2 over 4 minus 2. That's what mean value theorem says. F of 4 is 16 minus f of 2 is 4 over 2. So that is just 12 over 2, which is equals to 6. So this is true. We just use mean value theorem. Okay? This guy is another bad question. I got so confused by this first few words here. The rate of change of the temperature, T. So you would think, because they wrote it like this, that they're saying T is the rate of change of the temperature. No, they're saying T is the temperature. The rate of change of the temperature is derivative with respect to time. Okay? That's the confusing part here. Okay, let's continue. Of a coffee is proportional to the temperature difference between the coffee and the surrounding air. Suppose that T equals 0, temperature is 180, and decreasing at a rate of at 5 degrees Fahrenheit per minute, which the following is a correct model for the temperature of the coffee. Okay, so that's why I got so lost, because if this is T, then derivative of T with respect to time is the second derivative of the temperature. So how fast that rate of change of the temperature is changing. But that's not the case. I believe this is actually saying this T is temperature, and this other rate of change is the derivative of capital T with respect to time. Oh, okay. It was very confusing. It took me like 3 whole minutes to figure that out. Anyway, it's saying that dt, d capital D over dt, is proportional to temperature difference. So proportional is just some constant k to the difference between the coffee, so let's say that's T, and the surrounding air minus 70. Okay, something like that. Okay, and then suppose at T equals 0, the coffee has temperature 180 degrees. And actually, I'm not sure that's even helpful. So I didn't fully understand this, why they gave all that. But anyway, we know that just by the first sentence, it should look something like this. Okay? And we know that K should be negative because the change in temperature is decreasing. I mean, the temperature is decreasing, so the derivative should be negative. So we can immediately eliminate the positive K's, which are those two, okay? So, what is next is either this or this, okay? So, just by I actually didn't get how they would get 22. Is it something to do with this? 180 divided by... No, it's 180 minus 70 divided by 5. That looks like 1 over 20. That looks like 22. Okay, so I'm thinking out loud again. Anyway, but we eliminated these, so we're trying to find this. So they give this at t is equal to 0. This guy is some... change of the temperature. The temperature is changing, so it should be like something like that. So, okay, okay, let me rewrite this. Temperature is still changing with respect to time. Okay, and now let's use this information. It's decreasing at a rate of -5. So the rate, that means derivative, -5 is at t equals 0. That was 180, right? So -5 is equal to k, 180 minus 70. Okay, so -5 is equal to k times, that's 110. K is minus 22, 1 over. Okay. So then we have C as an answer. Okay, so that's how we use that second sentence. Okay, so once again, I knew that the rate of change of the temperature, which is actually d capital D over dt, is not T. That's the confusing part of this wording. Whoever, again, wrote this question did not do good. That derivative is proportional. So remember, I don't know what grade you learned this. Proportional is always, we note it with K. Proportional to the temperature difference between coffee, tea, and the surrounding air, 70 degrees, okay? Temperature is still a function of time, so it's like that. And then they give us that t equals 0, the temperature is 180, okay? And then the rate of change is -5, so we solve for that proportionality constant was -1 over 22, so that's our answer. Okay. And I believe this is the last problem, and I'm running out of battery also, so perfect. Timing, okay. We're given that cylinder has radius r, height h, volume and surface area is given by this, dimensions of the cylinder with max volume we want to find. Okay, so we want to maximize volume, dV by d something, okay? Here we have two variables. Is radius changing with respect to... Actually, this is not related rate, so this is optimization. So remember, we need a primary equation that optimizes what we want, so they give it to us. Primary equation, secondary equation, that's to help us eliminate, if there's multiple variables, and eliminate it down to 1. Okay, that's the technique. So we are given that, so there are two variables here, so we have to use this guy somehow to eliminate one of the two. Okay, and we're given that if the surface area is 6 pi, okay, then let's use that formula that they gave us. Okay, so that would be 3 is equal to r plus h. So we get 3 is equal to r squared plus h and r. Okay, so let's solve for h. That'll be h is equal to 3 minus r squared divided by r. Okay, so now we can write v is equal to pi r squared times 3 minus r squared over r. Okay, now we eliminated one variable of the two. So now let's simplify. That's just pi r 3 minus r squared. Or it's just pi times 3r minus r cubed. Okay, so now we can differentiate v with respect to r. Let's do it over here. dv dr is equal to, pi is just a constant. The inside would be 3 minus 3r squared. And we want to optimize this, set it equal to 0. Okay, we can simplify. It'll be 3 pi 1 minus r squared is equal to 0. Or 3 pi 1 plus r, we can factor 1 minus r is equal to 0. Okay, so we know our solution is radius is equal to 1. Radius cannot be negative, so we can eliminate that solution. So radius is equal to 1. Are we given units? We're not given units. Okay, so r is equal to 1. That's one of our dimensions. We need h also. We have h over here. So h is equal to 3 minus 1 over 1. That's just 2. Okay, so that's how you solve this one. This one was not bad at all. Okay, so hopefully this video helped, and I really hope that I don't give you, especially this question. This was so confusing because they say rate of change in temperature is T, or you could read it like that. Instead of temperature is T. Oh, this is my scratch paper of my first attempt, but it's the same thing. Okay, where did it go? I don't remember where I put it now. Okay, that's fine. And then this one was also confusing because they assumed that you know that this is a differential. So hopefully whoever writes the exam problems gives you more clear instructions or descriptions, okay? But anyway, hopefully this video helped you to see something like this. I don't see differentials that often, so this is kind of new. And then, yeah, the other one was also kind of more conceptual too. Okay, yeah, that's it for this video. So hopefully, once again, if this video has helped you in a way, please hit that like button and please subscribe to see more videos like this. See you in the next video. Bye.